Hello everybody, so this is the first video associated with Chapter 3 of Introduction to Quantitative Finance. So in this chapter, what's going to happen is we're going to present another model for option pricing, which is called the Black-Scholes model and is named after the creators of this model. So in chapter 2 we had a pricing model for derivatives and options which relied on trees. It was a discrete time model, and the tree model assumption is a bit oversimplistic. So in this chapter we'll refine that model to get a more realistic but a bit more complex result. So for this chapter, the theory is much more complicated. We won't go in depth through the theory as this is typically done in most more advanced courses, but we'll invoke principles we've used and formally demonstrated in the previous chapter, and we're going to use these principles to obtain the resulting formulas for option pricing. Okay, so in this chapter, we're going to study a continuous time model, the Black-Scholes model, where time flows continuously. So instead of having discrete time steps, 0, 1, 2, 3, etc., time will flow continuously between an interval 0 and time capital T. Okay, so this is a key difference between the model presented in the current chapter versus the trees presented in the previous chapters. So here we're going to introduce a bit of notation first. So omega here is the sample space which contains all possible realizations of random outcomes. Okay, so for example, if you've seen that in probability class, but if you roll a dice, then there are 6 possible outcomes, so you can call them omega 1 until omega 6. So omega is the set of all possible outcomes which can happen, and P is a probability measure which assigns probabilities to events, where events are subsets of omega, are collections of possible realizations or outcomes. Okay, so P assigns a probability to the various possible events. Okay, so here P in this chapter, again, it will be referred to the physical measure, which is analogous to the physical measure P we have seen in chapter 2. So here we're going to do a bit of mathematical definitions here. We define a continuous time stochastic process S being a sequence of random variables indexed by time. Okay, so S, a stochastic process, is a set or a sequence of STs where each of these STs are random variables, and T is an index flowing continuously between 0 and time capital T. Okay, so for example, what's the difference between a stochastic process and a random variable? A random variable would be a value of something at a given point in time, whereas the stochastic process would be the set of all the value of a given phenomena, but at all points in time. So for example, if I tell you the price of a stock at 9 a.m. on Monday, this is a random variable because it's at a fixed point in time. Whereas if I tell you the set of all prices of this given stock throughout the week, then this is a stochastic process because it's a collection of random variables, each associated with a given time point. So a quick remark here, a continuous time stochastic process S can be represented as a function of this form. It's a mapping or a function which takes as an input an element of the interval 0t, so a time point within this interval, and takes also as an input a random outcome in omega and returns a real number. Okay, so for example, if we go back to what we were saying, the stochastic process would be the set of all prices throughout the week of some given stock, let's say the Microsoft stock. Then once we fixed T, so let's say we say T is Tuesday 10 a.m. and if we fix a random outcome, then, well, rounding outcome, we can say that the stock price has gone up by 10% or something like that. Then this returns a real number, which would be the value of the stock at this point, given this random outcome had occurred. Okay, so a stochastic process can be seen as a function of this form. So if you specify a time point for the process and a possible random outcome, then you would get the value of that the associated random variable at that time point for this outcome. Okay, so now we said a stochastic process is a function with two inputs, one time point and one outcome. So what we can do is we can fix the random outcome and then let time flow. So if we fix the outcome but we let the time vary, then we get a single dimensional function of time, which we call a path. Okay, so maybe let's draw a little picture here. So maybe this is T, and here ST can be the price of a stock through time. So a path here is would correspond to a sequence of price of the stock through time. Okay, so this is an example of a path. We fix the random outcome and we let time flow through, time vary here. Okay, so this would be one path. Another path could be, whoops, let's start by at the same place, but another path could be something like that. Okay, so each path correspond to a possible scenario or a possible random outcome. Okay, so yeah, omega, I say random outcome, but I think maybe it's clearer if you understand it as a possible scenario. Okay, omega, possible scenario. Furthermore, we can do the opposite. So let's erase this. We can take a stochastic process, fix the time. So let's say instead of being the set of all prices through the weeks, we fix the time. So we can say the price of the stock at Monday 10 a.m. and we can let the scenario vary. So here, if we let the scenario vary, the price of the stock at this time point becomes a random variable. So a stochastic process for which we fix the time, if we take a single time point, then it becomes simply a normal random variable. Okay, so when we consider a stochastic process, if we fix the scenario but we let the time vary, this becomes a path. Conversely, if you fix the time and you let the scenario vary, this becomes a random variable. Okay, so here we're gonna use some notation here. FST. This guy here, we won't define it formally. This is in more advanced class. You're gonna see this is called a sigma algebra, and it has a very precise mathematical definition. But here in this course, we won't go through these fine details, so we'll keep it at a more intuitive level. So here, FTS, we're gonna say this denotes the information generated by the stochastic process S up until time t. Okay, so when we're gonna use this symbol in conditional expectations, so for example, if we calculate a conditional expectation given FST, this is equivalent to saying that we condition given all values of the process S until time t. Okay, so it's assuming we know the value of process S up until time t, and then future values of the process after time t are unknown in the conditional expectation in that case. Okay, so FTS corresponds to the information generated by the stochastic process S up until time t. Okay, so now the construction of the Black-Scholes model, we're going to see in this chapter, it relies very heavily on what we call the Brownian motion. Okay, so before defining the Black-Scholes model, we must define what is a Brownian motion. So Brownian motion, which we will denote by W, is a continuous time stochastic process. Okay, so we use the previous definition of a stochastic process to define Brownian motion. And that stochastic process has the following four properties. Okay, so first property, its initial value at time 0 must be 0. AS means almost surely, means with probability 1. Okay, so the process starts at 0 with probability 1. Second property of the Brownian motion is called the independent increments property, which says that if we have 4 time steps, t1 smaller than t2, smaller or equal to t3, smaller than t4, then the increment of the Brownian motion between t3 and t4 is independent from the increment between t1 and t2. Okay, so by increment, we mean the variation of the Brownian motion. Okay, so if we draw a little picture to make that more clear, here let's say we have, this is t1, t2, sorry for the writing, it's a bit bad with the software. This is t4. Okay, so if we have that, then the variation of the Brownian motion over this interval here is independent of the variation of the Brownian motion here on this other interval. Meaning that for any two intervals that are disjoint, okay, maybe the t2 and t3, they can be the same value, but otherwise, if the intervals are disjoint, then it means that the variation of the Brownian motion in these two increments must be independent, regardless of what these two intervals are. Okay, so this is the intuition behind Brownian motion. So, okay, maybe some more intuition. Brownian motion, we're going to see next that it's used to represent the evolution of the price of a stock in the Black-Scholes model. Okay, so the idea about this second point is we want to say that the return on a given day of the stock or a given period will be independent from the return on some other period. Okay, so to be able to say that, we're gonna invoke this property of Brownian motion, which is independent increments. Third property of the Brownian motion is that its increments are normally distributed. Okay, so for any t greater than s, any time point t greater than time point s, the variation of the Brownian motion between s and t. Okay, so if we draw a picture here, this is time s, this is time t. Then the variation of the Brownian motion over this interval has a normal distribution with mean 0 and variance t minus s. Okay, so the variance of the variation of the Brownian motion is proportional to the length of the interval, whereas the mean is always 0. And finally, last property of the Brownian motion is continuous paths with probability 1. Okay, so if you draw paths of a Brownian motion, so let's say this is t, this is wt here. For a Brownian motion, paths are always continuous. Okay, so it starts at 0 here. So you always have something like this for a Brownian motion. It's impossible to get, maybe, can I change color? Okay. It's impossible to get something like this where you have a jump here. Okay, so the blue path is not a path that can be produced by Brownian motion. So with probability 1, all paths of the Brownian motion look like something like the red one, okay, not the blue one. So paths of a Brownian motion are always continuous. Okay, So what does Brownian motion look like in practice? So I've used the R statistical software to generate, or is it MATLAB, or I don't remember, either R or MATLAB, to generate the path of a Brownian motion, and it looks like this. Okay, so this is a path generated from a Brownian motion. Okay, so here the path starts at 0, as we said, and then it varies continuously through time. Okay, so although it's continuous, the paths are somewhat bumpy. Okay, so it, it's continuous, but it's not smooth. Okay, so paths of the Brownian motion are very bumpy. Okay, and this is a weird property of the Brownian motion. So if you do more advanced probability classes and you study more in depth the properties of the Brownian motion, you will get to learn that from the definition, paths must be continuous with probability 1. But the weird part is that they're non-differentiable everywhere with probability 1. Okay, so with probability 1, it's continuous everywhere, but for any point of the path, it's not differentiable. Okay, you cannot never find the derivative of a path of a Brownian motion. Okay, so this is a very strange property. Okay, which gives the very bumpy or very erratic behavior to the Brownian motion. So for the remainder of this chapter, W here will denote Brownian motion. Okay, so now we're gonna jump to finance and start highlighting the Black-Scholes model. So again, we're gonna consider an a market with two traded assets, similar to what we did in the last chapter. The two assets are the following. The first asset is a risk-free asset, which we denote by B. And the second asset is a risky asset denoted by S. So the risky asset, often it's a stock. And this stock is assumed to pay dividends at a continuous rate. Okay, so all the theory can be worked out for discrete dividends, but this complicates formulas a lot. So for the sake of this course, we're going to assume a constant rate of dividends, which is denoted by Q. Okay, so Q is the dividend rate of the stock in this chapter. So what this means here, it means that for each infinitesimal time period from t to t plus delta t, the infinitesimal dividend paid is stq delta, which is paid at time t plus delta. Okay, so instead, to be a bit more rigorous, we could have said that this would be proportional to st plus delta instead of st, but since delta is infinitely small, this is pretty much the same thing. Okay, so we have two assets, one risk-free asset and one risky asset, which is a stock, or can be something else, but we're going to think of it as a stock, and it pays continuous dividends through time. Okay. Moreover, the rate will be constant over the time interval. Okay, so the dynamics of these two assets in the Black-Scholes model are as follows. Okay, so BT, the risk-free asset, it's assumed to grow continuously at the risk-free rate. Okay, so its time t value, it's simply the exponential of the risk-free rate times t. So this grows exponentially at a constant rate. The second asset, the stock, is assumed to have the following dynamics. So here, the time t price of the stock is assumed to be its initial price times the exponential of, okay, so this guy is a constant, mu is a constant, minus 0.5 sigma square. So sigma square is also a constant. Mu and sigma are parameters of the model, times t, plus the constant sigma times the time t value of the Brownian motion. Okay, so here mu, sigma, and r are constants that are parameters of the model. Okay, so what does this guy look like? Well, this is a constant times t. So if we plot this this first term, the first term looks like this. The first term is simply increases through time linearly, whereas the second term here, sigma wt, it's the Brownian motion multiplied by a constant, so it varies like something like this. Okay, so this first term represents the overall trend of the stock price, which grows linearly. And here the second price represents fluctuations, which allows the price to depart from its trend. Okay, so stock prices, we all know they vary randomly in the sense that they're not very predictable. So for that reason, we need to add an element of fluctuation or randomness. So this is done through the Brownian motion here. Okay, now one question you might ask yourself is, why do we write mu minus 1/2 sigma square? Why not just put a mu here to make things simple, since this is already a constant? Well, the answer to this question is the following. So when you're going to do the exercises, you're going to see, or you'll have to show that the expectation of st will be equal to s0 exponential of mu t. Okay, so having this constant here where you subtract by 1/2 of sigma square, this allows you to get the following interpretation for the parameter mu. Mu is the average growth rate of the stock on a log scale. Okay, so this is why we have this this constant here. Okay, so this is an intuitive model in the sense that stock prices, they have a long-term trend. So here, this long-term trend, we said this term here is linear, but because it's the exponential, then the overall trend of the stock will be exponential like this, which is what happens in practice. But then you have an offsetting term here, which creates some random fluctuations and allow the stock values to depart from its trend. Okay, and here WP, we said it's a Brownian motion, but the P denotes the fact that it's a Brownian motion under the physical measure P. Why am I saying that right now? It's because later on in the chapter, we're going to introduce a measure Q, which will act as the risk-neutral measure, similarly to what we've done in the previous chapter. So we'll have to talk about what happens under P and under Q. Okay, so WP is a Brownian motion under the probability measure P. So under this model, we can show some properties of the underlying asset, or the risky asset, because, so if we go back one slide here, what's inside the exponential, this is if we fix time t, this is a constant plus we said wt had a normal random variable times a constant, so this is still normal. So the risky asset price is a constant times the exponential of a normal random variable. So it's straightforward to show that this has a log normal distribution. Okay, so if you have a normal distribution, you take its exponential, this becomes log normal. Furthermore, as we mentioned, it's possible to show that the expectation of the stock price or the risky asset price at time t is its initial price times the exponential of mu t. So mu can represent the average growth rate of the stock in this model. Okay, so when you do exercises, you'll have to manipulate this this model a bit more. You'll have to for example, here we give the mean, but you can also calculate its variance, etc. So I invite you to spend some time on the exercises to make sure you understand this model well and understand how to calculate moments and probabilities that the stock is greater than some threshold, or moments like its variance, its expectation, etc. Okay, so make sure you're comfortable with this model through the exercises. Another property that can be shown from this model, okay, so this, I suggest you pause the video and try out to show this. Okay, so it's not very complicated. You can just substitute. Okay, well, first I'm going to read the property. It can be shown that log returns. So what do we mean by log return? It's the log of the ratio of the stock on one time t2 versus the value of at another time t1. It can be shown that these log returns are normally distributed. Of course, assuming t2 is greater than t1. Okay, so they're normally distributed. The mean of the log return is that constant here, mu minus half of sigma square. So this is the constant we saw earlier in the model, times the length of the interval. And the variance is assumed to be sigma square times the length of the interval. Okay, so the mean and the variance of the log return are both proportional to the length of the interval, but the distribution of the log return is normally distributed. Okay, so again, I suggest you to pause the video at this point and try out to show this. Okay, so this is not very complicated. This can be done in a few lines. How you do that, you can substitute the value of ST2 and ST1 by their definition. So you can if we go back here, we can replace T2 or T1 here instead of T. Use this formula, plug it in the log return formula, and then see what happens to show this property. Okay, so please pause the video, try to show this. Okay, this will be very instructive. And finally, one last property of risky asset prices is that their paths are continuous. Okay, so the price of the risky asset is roughly the exponential of some linear transformation of the Brownian motion. So because the Brownian motion is continuous, when we take the exponential is a continuous function. So the exponential of the Brownian motion is still something continuous. So this is why we have continuous paths of the Brownian motion. Okay, so now we've outlined the dynamics of the assets on the market. What we're going to do next is we're going to price or try to price financial derivatives who have the risky asset as an underlying asset. Okay, so in particular, we'll want to price a derivative which has a time capital T payoff denoted by psi of st. Okay, so the payoff of this option or a derivative, we're going to assume that it's a function of the underlying asset at maturity. Okay, so you can think of maybe a European option as an example of derivative which provides a fixed, not a fixed payoff, but a payoff at a fixed time capital T. So how are we going to price this option? Well, as we mentioned earlier, to work out the entire theory is it takes a lot of time, details, and advanced mathematics, so we won't do that here in this course. However, what we will say is that the same principles that we've used in Chapter 2 also apply to this model in Chapter 3. Okay, and what principles are we talking about here? We are talking about the fact that derivatives are priced through replicating portfolios. Okay, so in the Black-Scholes model, for any derivative, you can always find a replicating portfolio. So the price of the derivative will be given by the price of the replicating portfolio. And furthermore, as in Chapter 2, the price of the replicating portfolio can be obtained by a risk-neutral evaluation formula. Okay, so combining all these facts using the same theory than in same principles at least than in chapter 2. Proofs are omitted, but we're going to still use them in this chapter. The price at time t of a derivative is the following. It's the discounted expected payoff of the option given the available information at time t. But again, the expectation is not under the physical measure, but rather under some risk-neutral measure. Okay, so the risk-neutral measure, again, here is a measure, probability measure that has no physical interpretation. It's just an artifact that is convenient for calculations to obtain the price of a replicating portfolio, and thus to price derivatives. Okay, so here again, this is what we call the risk-neutral evaluation formula. It says that roughly that the time t price of a derivative is its expected discounted payoff given the current information, but the expectation is under a risk-neutral measure. So now the question is, in that model, what does the risk-neutral measure look like? Okay, so in the previous chapter, going from the physical measure to the risk-neutral measure, until that what was changing is the probabilities of scenarios. So you still had a tree structure under the physical measure, but the probabilities to go up or down, they were changed when we went to the risk-neutral measure. Okay, so here what's going to happen in the risk-neutral measure, this is an important question, and we'll discuss that subsequently. Okay. Now, one quick note here, I haven't discussed that in the previous properties, but it's possible to show that the underlying asset price, so the price of the risky asset in the Black-Scholes model, has what we call the Markov property. Okay, so again, I don't necessarily want to go into the details about this. So for people who've done classes on Markov chains, you can have a better grasp of what this means. But it's possible to show that the Brownian motion has the Markov property. And in intuitive term, it means that if you're at time t and you want to forecast future values of the process at times beyond t, the only relevant information is the current value of the process at time t. So all previous prices or all previous values of the process become irrelevant once you know the last value of the process at time t. Okay, so Markov process would mean that if you try to forecast stock prices in the market, and if the stock prices are Markov processes, the only thing that could help you out doing the forecast is the current price of the stock, and previous prices would not be useful for such purposes. Okay, so that would be an example of an application of Markov processes to stocks. Okay, so for that reason, it is possible to show that the conditional expectation here, when we condition with respect to the current information on the market, it's possible to show that this conditional expectation can be written as a conditional expectation with respect to only the current time t price of the stock in the market. Okay, so the only relevant information to predict payoffs or generate scenarios of the payoff in the future is the current stock price. Okay, so this is why we can replace in the risk-neutral valuation formula this conditional expectation here by the current value of the stock. Okay, so it means that the price of a derivative is the discount factor times the expected payoff conditional on the current value of the stock under the risk-neutral measure. And here, this conditional expectation, again, we haven't studied properties of conditional expectations, but it's possible to show that this conditional expectation is a function of two parameters. It's a function of time, of course, because when time small t varies, this quantity will vary, but it's also a function of the stock price. Okay, so why is it a function of the stock price? Well, intuitively, if the current value of the stock price um, fluctuates, then we'll have a different expected value for the payoff. Okay, so for example, if we have an option with strike $100, then its expected payoff will be different if the stock price is currently $120 or $30, for example. Okay, so this is why the price is a function of two quantities in that model. The price is a function of the time. Of course, as time varies, the price will vary, but it's also a function of the current stock price in the market. Okay, but now we discussed that earlier. We have to determine what happens under the risk neutral measure in this model. Okay, so to do that, what we're going to do is we'll define a new stochastic process and we'll provide the rationale after for about why we defined it. Okay, so we're going to define a new stochastic process through the following transformation. Okay, so the time t value of the process, which we denote by WQ, it's defined as the time t value of the Brownian motion under P, plus here some offsetting constant, which will be mu minus the risk-free rate minus the dividend yield divided by sigma, okay, times t. Okay, so again, this is mysterious, but for now, let's just accept this. Okay, so we have a Brownian motion under P, and we can offset the values of this Brownian motion by these constants. Okay, so for each different t, the constant changes through the value of t here to define a new stochastic process. Okay, so under P, under the physical measure, this new process WQ is a Brownian motion plus some linear term trend. Okay, so we'll use this formula to rewrite the dynamics of the risky asset in terms of WQ instead. Okay, so if we go here, the first line here, this is the dynamics of the underlying asset in the Black-Scholes model. Okay, so S0 times the exponential of our linear trend plus sigma times the Brownian motion under P. And then using the new process we defined, we saw that WP is WQ minus that we're the constant here. Okay, so if we go back one slide, WQ here, sorry, WP is WQ minus this whole constant here. So we can make that substitution here. And then what's going to happen, the sigmas here and here, they would cancel out. So here you would get t times this constant. The mu t here will cancel out with this one. And this new term, we can take it out of this parenthesis to become the constant. So here we can go from here to here through only simplifications and rewrite, like reordering the terms. And this leads to the following. So st is s0 times the exponential of, still this is a linear term. Okay, this is a constant times t, where here mu is replaced by the risk-free rate minus the dividend rate plus sigma WQ. Okay, but here now, WQ, remember that under P, it's not a Brownian motion. Under P, it's a Brownian motion plus a linear trending term. However, it can be shown, again, let's omit all the theory. This is, if you want to know more about this, you can follow the MACF2 course, which is a more advanced financial mathematics course. But it can be shown that in our Black-Scholes market, that risk neutral measure, well, it exists, and moreover, it's unique. Okay, so there are no there's only a single possible risk-neutral measure we can use to price options. And furthermore, under this risk-neutral measure, the process WQ is a Brownian motion. Okay, so let's repeat that. Under the physical measure, WQ is a Brownian motion plus a trend. However, under the risk-neutral measure, WQ is a Brownian motion with no linear trends. Okay, so this is the important thing to remember. So going back in the previous slides, we see that here, this quantity, this is an expression of the stock price with respect to WQ. And under the risk-neutral measure, this WQ is a Brownian motion. So it means that the dynamics of the stock is still what we call geometric Brownian motion under Q. So it's still the same type of model. But what changes here is that the constant mu was replaced by R minus Q. So this means that by going from the physical to the risk-neutral measure, the stock price dynamics remains the same, except the linear trend term has a different value. Before it was the expected growth rate was mu under the physical measure, whereas now under the risk-neutral measure, the expected growth rate is the risk-free rate minus the dividends rate, dividends yield. Okay. So summarizing all the results and collecting them together, we have the following theorem, which is the main result used to value derivatives in the Black-Scholes market. Okay, so here in the Black-Scholes market, the no arbitrage price of a derivative, okay, so the price will be denoted by FT S of t. So the price depends on time, of course, and on the price of the underlying asset. The price of a derivative which provides a time t payoff of psi s capital T. So assuming the payoff is given at the maturity time capital T and is given by this formula, so it's a function of the risky asset at maturity, then the price of the derivative must be of this form. The price of a derivative at time t must be equal to the discount factor between small t and capital T of the expected payoff given the current value of the underlying asset. But here this payoff, as we said, it's not under the physical measure, it's under the risk-neutral measure. And furthermore, under the risk-neutral measure, what is the dynamics of the stock? The dynamics of the stock still has the same form that we had earlier. Okay, so the price at time S capital T can be expressed as its times ST price times the exponential of, this is our new constant under Q, so it's the new growth rate, R minus Q, minus this term, 1/2 of the variance, or not the variance, but the sigma square parameter times capital T minus small t, plus sigma times the increment of this process WQ. But here WQ, it's not the original Brownian motion under P, it's the new process, which is a Brownian motion under Q. So this is the main result to price derivatives. Okay, so once you understand this result, you can use it to price various derivatives in the Black-Scholes market. Okay, so here this is a very generic formula for all derivatives which provide a payoff at time capital T. Well, in the next video, we're going to give particular cases. So what happens when psi has the form of the payoff of an option? So how do we price options? Well, we're going to apply this principle or this formula to more specific cases of options in the next videos. Okay, so before we stop that video, we have some quick observations about what the previous result we obtained. So under P, the price of the risky asset had the dynamics of what we call a geometric Brownian motion. So geometric Brownian motion, it's simply the exponential of a linear transformation of a Brownian motion. Okay, so under P, the stock had a geometric Brownian motion dynamics with average growth rate mu, whereas under Q, the price of the risky asset still has this geometric Brownian motion dynamics, but here the rate mu, average growth rate mu, under P is replaced by an average growth rate of R minus Q, risk-free rate minus the dividends when we go to the risk-neutral measure. Okay, so because of that, this entails that the price of any derivative does not depend on the parameter mu. Okay, so the average at which the stock price grows through time doesn't appear nowhere in pricing formulas for derivatives. Okay, so this again is counterintuitive, but it's the same thing that happened in Chapter 2. So in Chapter 2, we saw that the parameter P, the probability of an upward movement, had no impact on the price of options. And here in this chapter, we have the same type of phenomenon. The parameter mu has no impact on prices of options, which is surprising at first, but this is what happens. All right, so we'll stop the video here. So I'll see you shortly for the second video of this chapter. Thank you. Have a nice day.